I wish to thank the organizers, Kamal and Bowman, of this memorial session for giving me an opportunity to deliver lifelong observation of the impact of the Tatsuo Itoh Lab on international microwave community. I'm C.K. Clive Tzuang, Emeritus Professor from National Taiwan University, also Chair for the IEEE Taipei Life Member Affinity Group. The speech will be reported to IEEE Region 10 Life Member Committee as part of activities of Taipei Life Member Affinity Group. Join IEEE MTDS. This will be one wisest investment you ever made. Most materials presented here were downloaded from IEEE Explorer. Also, I wish to extend my sincere apologies to authors of the Itoh Lab for not mentioning their relevant works to keep this talk brief and concise. This presentation is mainly from the scientific perspective of guided waves on seeking solutions for complex propagation constants in hope of offering audience of deeper view into the research world of Professor Tatsuo Itoh. The second slide outlines the talk chronically. I first met Professor Itoh on one Thursday morning in July 1983 at UCLA Extension course. 2 months prior to the extension course, I was in Dallas IMS attending a session when Itoh Lab presented the computer-aided design, CAD, of finite filters based on true 3D electromagnetic field solutions. If I may fast forward the time to 2015, when I published the work on guiding properties of SIW, substrate integrated waveguide, from microwave to terahertz on transaction on MTT, you may see here the definition of the generalized scattering matrix. Defined as the refracted wave of mode m divided by the incident wave of mode n between the reference plane 1 and 2, which constitute a unit cell of the periodic SIW structure. Here and here. We see that SIW is a partially open guided wave structure. To assure the leaky surface wave reaching the edge not to be reflected back to the substrate, the supporting substrate is tapered on both sides of the SIW, here and here. The results show the frequency versus normalized propagation constant, or the so-called slow wave factor, with the 3 space harmonics, -1, 0, and +1, symmetric on the vertical axis of operating frequencies. Even though the SIW supports the right-hand type of the propagating mode, we see the space harmonics couple and result in stopping at higher frequencies in the form of complex mode, somewhere along here and here and here. The results shown here are important for the audience to understand the works of Itoh Lab, because the complex propagation constant derived here account for all loss mechanisms, including material losses, substrate plus finite conductivities, radiation losses, here primarily the surface wave leakage into the substrate, then to the air. I joined Itoh Lab in 1984 when the spectral domain analysis SDA of 2D guided wave structures was still the main research area, I was given two tasks: formulating finite element method and mode matching method. For the latter, I received many helps from Dr. Fukuoka. So grateful. Tackling slow wave structure built on MMICs. At the same time, the problem of the existence of complex mode in box lossless guided wave structure, such as thin lines, E-plane structure, and box coupled microstrip H-plane structure began to emerge. Since, for example, the thin line filter design CAD program needed to incorporate the complex mode to account for more completeness without sacrificing the accuracy. An important notion should be pointed out. Professor A. A. Oliner announced the finding of the complex mode in open microstrip structure in the same 1986 IMS session when I presented the dispersive slow wave characteristics of an MMIC-based transmission line. The radiation characteristics of the new findings by Oliner were best categorized as a leaky mode or a leaky wave type antenna. At the end of this talk, the audience may appreciate the fact reported by the Itoh lab that leaky wave antenna can be synthesized without scanning blindness typically seen in beamforming arrays. The research on slow wave structures continued to the periodic type slow wave devices to the end of 1990s. Then, the Itoh lab's results began to explode like the early volcanic eruptions around 1990s. Here I show three examples, all related to the previous works. At the same time, work on 3D finite difference time domain started and continued to the next decade. The impact of Itoh Lab's results is like volcanic eruptions, which grew bigger and bigger in the next decade and beyond till around 2005, identifying three main fields of microwave engineering studies, namely active integrated antenna, photonic bandgap or electromagnetic bandgap structures, composite right-hand left-hand metamaterials, the unusual guided wave behaviors arising from mostly the periodical structures were grouped into the class of metamaterials around 2005. I call the period from 1980s to 2005 a 25-year rush to the fundamental research of the guided wave devices, circuits, and systems, which include antennas, a golden era that any microwave researchers, scholars, engineers may dream of working in the related subjects at that time. On the left of the view graph is the syllabus of the theory of electromagnetic fields, lectured by Professor Itoh in spring 1985. On the right shows one page of lecture notes, page 19, highlighting the ultimate goal of the electromagnetic field analysis is to explore the microwave circuit behavior with impedance concept. Ichi was the first PhD graduate. The 3D CAD design of microwave and millimeter wave filters may best represent the arrival of the dawn of the Itoh lab, and best illustrate the powerfulness of managing guided wave field theory for practical microwave circuit designs. Note on the middle page that the sub-matrices of the S matrix are also generalized scattering matrices to account for the effects of microwave junction discontinuities. In mid-1980s, I wish to point out two results worthy of attention. Tetsuo reported a synthesized miniaturized through-wave structure is possible and feasible, as he reported in the 1987 MTT transaction paper, in which the alternating high-low characteristic impedance lines in cascade would make a synthesized transmission line of through-wave factor greater than 11. The wave speed is then at 1/11th of the free space light speed. Also notice that the mathematical procedure to derive the expression for obtaining complex propagation constant is similar to that of composite right-hand left-hand transmission line in the last few graphs of this talk. Also notice on another report that the spectral domain method demonstrated for the first time its ability to obtain a complex mode for microstrip enclosed in a magnetic box as seen in the Huang's paper. The region where complex modes start to emerge were all from the type of two closely coupled evanescent modes, resulting in 1 alpha imaginary part or attenuation constant and 2 beta, that is the real part of opposite signs, to maintain equal number of modes. Here are evanescent mode. This is the complex mode. The 1989-1990 timeframe signifies the beginning of early volcanic-like explosions of research results from the Itoh lab. Phenomenological approximation of transmission line losses for over 6 decades of operating frequency up to terahertz had been demonstrated for its applicability for obtaining both attenuation constant and phase constant. Followed by Chang's work on reporting an active bandpass filter realized by the hybrid MIC process. It is a coupled resonator filter type, and each resonator is identical, and its losses were compensated by the negative resistance. We see the inevitable losses associated with the transmission line circuits can be practically alleviated by introducing gain in the presumably passive filter circuit. Essentially, the example of RF gun oscillator power combiner has been successfully illustrated by the periodic insertion of gun oscillator at half wavelength interval signify the use of periodical structure to the next high level. The reported number of the combining efficiency is also phenomenal. In the 1990s, AIA active integrated antenna came to our attention initially. In that decade, we often wondered what the next big things would be reported by the Itoh lab in all major international conferences. Shigeo reported in 1993 the multi-element oscillator power combining through space, all integrated in one printed circuit board. Bill demonstrated the power combining of two amplifiers through space using antenna. as a power combiner. The antenna design was evidently no longer antenna alone. Rather, it incorporated the consideration of the impedance matching, radiation pattern, etc., all in a simple layout. Radisix, in the same year, stepped further in a sense using antenna for additional purpose, harmonic loading the power amplifier by properly adding a shorting pin in the middle of the patch antenna to increase the power added efficiency of the PA, thus increasing the EIRP of the active antenna array while without altering the radiation pattern. Canada reported a very efficient mode converter using Yaki antenna as a mode transition circuit from here to here, demonstrating a powerful and robust waveguide transition concept and technique for system integration of very high frequency electronics. In summary, antenna is no longer an antenna as it used to be. It is part of microwave electronic system. This is also true for designing LEO satellite array antenna transceivers today. Then, PBG, photonic bandgap structure, or later called the EBG, electromagnetic bandgap structure, and the applications emerged as early as 1996. Chen, in 1998, showed a typical patch antenna proximity coupled to a PBG-EBG structure made of an array of smaller patch, coupled two-dimensionally. It suppressed the surface wave excited by the patch, thereby improving the gain and efficiency of the patch antenna. Radisix, at the same time, demonstrated the use of PBG-EBG interconnect line here that allow the fundamental mode to pass while reflected the second and third higher order modes. The power amplifier, therefore, showed the efficiency was improved significantly. The work was followed by hands using a much shorter slow wave line on a UC-PBG ground plane, while achieving even a better result in improving PA efficiency. The work of Chen was extended to use two-dimensional so-called UC-PBG surface to replace the couple patch surface. And better improvement in antenna efficiency was also observed. Note that the UC-PBG surface displayed two stopbands here and here, while exhibiting the slow wave factor exceeding the theoretical limit of the square root of the relative epsilon, as shown here. They are all inside this area. All works done in EBG and PBG were considered metamaterials in the next decade. To me, the golden era ended near 2005, and before then, a very interesting Dickey wave or Dickey mode transmission line structure was reported by the Itoh lab in 2002. The Series C Xiang L composite right-hand, left-hand transmission line structure synthesized a frequency scan radiation pattern from the backward direction to the broadside direction to the forward direction continuously as the operating frequency increases. The corresponding dispersion curve are here. For the left-hand region, or the backward radiation region, the beta is negative. For the broadside, beta equal to 0, and for the forward direction, the beta is greater than 0. I consider this a magic finding that a transmission line of complex propagation constant may offer. Finally, may I make a conclusion? 2 weeks ago, Professor Sim of Fengjiao University showed me a slide which represented one layer of the stacked antenna array of the SpaceX Starlink antenna product shown here. I immediately recognized that Chen's work had been adopted for the product. So we can see the smaller couple patch array filling up the space between the radiating parasitic element. When I did a paper survey relevant to this product, I found, for example, a 2020 paper in IEEE Access report the similar structure. To my big surprise, if not an upset, the PBG-EBG structure was the main theme of the work of that paper, but not mentioning any trace of the most important prior work of the Itoh lab. Then I struck the light. A time for everything, from Ecclesiastes. For months, I could not conclude this talk. Now I may do so. Professor Tatsuo Itoh was an angel from heaven to me. Now he returned to where he came from. However, my entire career life was so easy because there has been a treasure island in the IEEE Explorer. That is a collection of papers from the Itoh lab. All were the results of the sacrifice and the pains that Professor Tatsuo Itoh had been through. I am sure all the contemporary engineers and scholars in microwave engineering profession will find professional life as easy as I was. Thank you, Professor Itoh, and God bless you all. Thank you.